In the second set of notes on section 10.2, we will be focusing on the following example problems. I'd like you to try these example problems on your own to the best of your ability. So you're going to pause the video, work through the sample problems, and once you're ready to compare your answers with mine, you can hit play. For example 1, we're given that segment AB is congruent to segment DC. Right away, we should be thinking that those are chords of the circle. And then we're also told that FE is equal to 12x minus 5. And then we know that EG is equal to 4x plus 19. We should be thinking about the theorem that says if two chords of a circle are congruent, then they are equidistant from the center. So this one was a pretty straightforward example, and that we just have to set those two expressions equal to each other. With that, we get that x has a value of 3, and since we want to find the length of segment FE, we can substitute that back in to get 31 for the final answer. For problem 2, we're given circle E. This time we know that segments FE and EG are congruent. Let's go ahead and fill in what we know. We know that segment DG, which is the small segment here, is 7x plus 2. And then chord AB has a length of 17x minus 8. Right away, we should be thinking about the fact that if two chords are equidistant from the center of the circle, then those chords are congruent. But notice we were not given the entire chord DC here. So we have to determine what that other portion is. Well, anytime we're drawing the distance from the center of the circle to the chord, it's perpendicular to the chord, and it also bisects the chord. So that means that the entire chord has a length that is double 7x plus 2. So it's 14x plus 4. Then we now know the lengths of both chords, and we can set those two expressions equal to each other. We find that x has a value of 4, and then we could substitute it back in to find that the length of segment DC is 60. For example 3, this one's a little bit more complicated. We're given that the perimeter of a regular hexagon is 48. Right away I'd be thinking, well, we know that we can divide that by 6 to find that each side of the hexagon is 8. Our goal is always to try to create right triangles. So once again, we know that the distance from the center of the circle to the chord is perpendicular bisector of the chord, so we can get that yellow segment has a length of 4. Now we're working with this right triangle. We know that this is 4, and that's all we know. But we want to find the distance from the center, so we have to find the other leg of that right triangle. I'd be thinking back to chapter 7 and work with the angles. We know that since this is a regular hexagon, all of the angles must add up to 720 degrees in any hexagon, but then since it's regular, we could divide it by 6 to find that each interior angle has a measure of 120 degrees. So that large angle right there would have a measure of 120 degrees. But when we constructed the hypotenuse of that right triangle, it bisected that angle, making it a 60-degree angle. So we have a 30, 60, 90 triangle. We know the side across from the 30-degree angle is 4, so the side across from our 60-degree angle is 4 radical 3, which is the distance from the center of the circle to the side of the hexagon. For example 4, we were given a 10 by 24 rectangle inscribed in a circle. So I'm going to label it this way, and I'm going to draw in from the center of the circle to the chord that perpendicular segment, so that's our distance from the center to the chord, which is going to bisect the chord as well. So we know that that side of 24 is going to be broken up into 12 and 12, and since we want to find the radius, we can construct our hypotenuse. Since one side of the rectangle has a length of 10, one leg of the triangle has a length of 5, since it's half of it, and then we're working with a 5, 12, 13 triangle. So that means that the hypotenuse is 13, which is the radius of our circle.